All right, so we're going to end this symposium with a bang. And to help us do that, we have Dr. Ali Sulaiman from the University of Minnesota here. I ran into Professor Sulaiman when I had some questions about, I guess, radios and radio signals coming from planets, and someone told me to go to talk to him. And when I started talking to him, I realized that there's a lot about planets I don't know. I'm completely really ignorant when it comes to that, and I learned a lot about Jupiter from him. And there's a lot more that I'd like to learn from his presentation today, so we're really fortunate to have him here give us this talk about the Juno mission, basically. Professor Sulaiman got his PhD from Imperial College in 2016, and then was a research scientist at University of Iowa for a while before coming to the University of Minnesota. And he's been here since, what, 2022. And with that, let's please welcome Professor Sulaiman, and I will hand the mic over to you.
Thank you, Demos. Well, thank you, everyone. Thanks for staying on. Today I'll be talking about the ongoing NASA's Juno mission, which is the only spacecraft in the outer solar system, so from Jupiter and beyond. So here we have an image of Jupiter taken by the James Webb Space Telescope. And over here is Juno, but not to scale. I put it up there. So there are lots of features that we can see here that are quite interesting, and I'll touch on these as I go along. But one of them, which is close to my heart, is Jupiter's auroras. So those are the northern and southern lights. So like the Earth, magnetized planets have auroras, and Jupiter actually boasts the most powerful auroras in the solar system. What's quite nice about this image in particular is you can get some sort of altitudinal extent to these auroras. So you can see they go quite high. And then, of course, the famous Great Red Spot. Unlike Saturn, which has a very dense and glorious rings, Jupiter has a diffuse ring. Here's a moon called Amalthea. And then out here is Io, which will be the center of attention of this talk towards the end. Now, Jupiter is the second spacecraft, sorry, Juno is the second spacecraft to orbit Jupiter. The first was Galileo, and that launched in the early 90s and was captured, I think, maybe 5 or 6 years after that. Lasted until the early 2000s. Juno was launched in 2011, arrived in 2016. And although it's a second polar orbiter of Jupiter, although it's a second orbiter of Jupiter, it's the first polar orbiter. So its orbits go from pole to pole, and for the very first time, giving us access to the poles and the auroras. So to get a sense of scale, Jupiter is the largest planet in the solar system, and much, much, much larger than the Earth. So you can see it has a mass that is 318 times that of the Earth. It has a length scale, so its radius is 11 times that of the Earth. And actually, the Great Red Spot, you can fit 3 Earths into that. And a Jupiter year, so the time that it takes to orbit the Sun, is 12 years. And it is at 5 astronomical units. So an astronomical unit is the average distance between the Earth and the Sun. So it's 5 times farther away. Now, one important thing to note is that given that it's so far away, from the 1/r² law, it intercepts 1/25th of the solar radiation that Earth does. Yet, it has an atmosphere and a climate that is highly dynamic. So you can see all of these sort of jet streams, vortices, eddies, the very scary Great Red Spot, which doesn't seem to go away. This is really a testament to how much energy there is within Jupiter, mostly coming from its rotation. But as I'll show in a moment, the atmosphere is actually very hot, even though it's very far away. And that's by virtue of the very powerful auroras. So they're able to deposit a lot of energy and drive the climate. Okay, looking at Juno close up, it's really a fantastic engineering project. So we're able to go so far away and not use nuclear radioisotope energy. Essentially, we're doing that with solar panels. And Jupiter really is as far as we can go with solar panels in the solar system. So anywhere beyond, you need nuclear power. And there's a whole multitude of instruments, about 10. So we can sort of classify those into 2. there's the so-called in situ instruments, which make local measurements. They make sort of single point local measurements, and that's essentially a suite of fields and particles instruments. So Juno measures electromagnetic fields, it measures electric fields and magnetic fields. Jupiter also has a very powerful intrinsic magnetic field. So the magnetometer makes this measurement here, and you can see it's right at the tip of the solar panel, and that's because you want to measure Jupiter's magnetic field, and you want to stay away from the electronics, which carry currents and themselves induce a magnetic field, okay? So you don't want to measure interesting frequencies and say, oh, we discovered aliens, there's some, codes that's being sent. That's most likely to be from the electronics. So we try and stay as far away from that as possible. Jade and Jedi measure energetic particles. So there's lots of charged particles in Jupiter's environment. Much of it is contained in the radiation belts, so similar to Earth, but much more powerful. And a lot of those charged particles stream into the polar regions and crash into the atmosphere and generate the aurora. So to understand the aurora, we need to measure the magnetic field and also the electric fields as well from the waves antenna and the radio waves, as well as the charged particles. Then we have the remote sensing instrument, which makes remote measurements from far away. So these are essentially across various wavelengths. So we have the microwave radiometer, and JURAM measures the infrared, UVS measures the ultraviolet, and also there's the radio and the optical or the visible from JunoCam. So we can make measurements across various different wavelengths, which is important to look at different depths of Jupiter and get a sense of what's going on in the atmosphere and in the interior. So a bit about the orbit, maybe if we start from the beginning. So it was launched in 2011 from Earth. And as you can see, it wasn't a straight path to Jupiter. There was sort of a series of so-called gravity assists where it went round and passed by the Earth. And the reason to do that is because it's the most efficient way to get out to the outer planets. So if you were to go straight, then if you wanted to accelerate, you'd have to burn a lot of propellant. But what you can do is you can take advantage of the orbital energy from planets. So it's effectively an elastic collision. So when a spacecraft flies past a planet, due to the very large mass ratio, the spacecraft is going to gain a lot of speed. The planet, on the other hand, is going to actually slow down, but the cost to it is going to be very, very small, again, because it's dependent on that mass ratio. So we don't have to worry about our years getting longer as a result of that. So effectively, it got there in 2016, and actually local time, I think it was July 4th here. So it's easy to remember when we got to Jupiter. And then, as you can see from the approach, when it got captured into orbit, it conducts a series of polar orbits, so whizzes past very close to Jupiter from pole to pole, and then has a very, very long periapsis away from Jupiter. It takes about 53 days to orbit, although that orbital period has been decreasing over time. And so here we're at the cusp of the prime mission, so which is now extended onto September 2025, and I'll talk a bit more about the prime mission in a moment. So looking closer at Jupiter, you can see how the orbit evolves, and that's because the gravitational field of Jupiter is inhomogeneous, and so that leads to changes or sort of precessions in the orbit. And what's nice about it is we don't need to burn propellant to do that. So for free, as we pass over the auroras, over time, we get a nice altitudinal coverage. So we get to explore the aurora over a whole range of altitudes. And you see we get to Jupiter. This is called the, this is the periapsis, and the farthest point is the apoapsis, which is very far away. But the periapsis, or the perijove, is about 1,500 miles above the cloud top. So really, really, really close. And it whizzes past so fast that it goes from pole to pole in a breakneck speed of about 2 hours. And this is also by design, because as I alluded to earlier, Jupiter's magnetic field traps particles which get kicked into very, very high energies. And this is called a radiation belt. It's a very stable, permanent region in space. And by conducting an orbit that's sort of over a very, very low altitude, it means we're able to duck and just about avoid the radiation belt. Although every now and again we see some signatures of degradation, but so far, so good. Okay, so what are the science objectives of the Juno mission? So they're threefold. One is to understand the interior of the planet. Essentially, what's the interior made of? And the reason why we'd like to understand that is because it gives us clues as to how the solar system was formed. So we believe that Jupiter was formed at the very, very early days of the solar system, and understanding the way mass is distributed in the interior gives us some idea of what kind of material was floating about early on in time. Now, actually, there's no special instrument to measure or to peer into the interior. So what they do is simply by looking at the radio waves that Juno beams back to Earth and look at the Doppler shift of the frequency or the wavelength in those radio waves. So essentially the way it works is you have Jupiter coming down from pole to pole, and you have the nice sort of pristine sort of computed orbit, which is a nice sort of elliptical trajectory. But in reality, Juno's trajectory wobbles back and forth, and it does that in response to the non-uniformity of mass in Jupiter. So certain parts of Jupiter are more dense than other parts, and so they pull the spacecraft more strongly than other parts. And so by looking at these wiggles, those are manifested as changes to wavelengths. You can think about the pitch of a train coming towards you, moving away from you. So looking at that in the wavelength, we can be able to essentially infer when Juno was pulled a little bit more or when it was pulled a little bit less, and get a sense of what the mass distribution is with latitude, okay? That essentially gives us clues as to how the interior is arranged, and tells us things like what the moment of inertia of the planet is as well, which is a proxy for the mass distribution. Okay? So again, no fancy instrument here. It's just by analyzing the radio waves that it beams back to Earth. And then doing some remote sensing measurement, we can get an idea of what's going on in the atmosphere, but also what's going on below the atmosphere, and getting an understanding of how the climate is driven, the atmospheric circulation, what atmospheric cells are present there. And you can see as Juno comes from the North Pole to the South Pole, the microwave radiometer essentially beams microwaves at 6 different frequencies. So it has 6 different channels, and the reflection of each frequency tells you something about a specific altitude. So by analyzing the beams that are being reflected from the 6 different channels, so the 6 different microwave frequencies, you can start to build a picture of how deep the atmosphere is, and essentially what's going on at the top versus what's going on to the bottom being as far as the microwave beams can go. And one thing that we learned fairly recently is that the Great Red Spot was surprisingly deep. So for very long, it was thought to be a shallow sort of hurricane, if you like, or a cyclone. But due to the microwave radiometer Juno, so if you sort of kind of build your onion here at the very top, this is just from the camera. The Great Red Spot's always visible. I mean, the James Webb Telescope sees it very easily. But looking from the different channels of the microwave radiometer, you can build a depth picture, 3-dimensional depth picture. And essentially what you can see is at the very bottom, the hot spot essentially is quite persistent deep. So actually this is a limit. It's likely that it goes even far deeper than that. 300 kilometers, if we think about it, compared to the Earth, that is enormously deep. And then over time, the circulation pattern at Jupiter is built. And so it's similar to Earth in some regards, but also different in other regards. So at Earth, these are what's known as the Hadley cells. Essentially, there are 3 Hadley cells per hemisphere. At Jupiter, there are many, many more, and they're smaller compared to sort of a latitude of Jupiter. And also they're a lot more curved, okay? So there's a lot more atmospheric dynamics going on at Jupiter compared to Earth. Now going outside the atmosphere, how far out? Quite far out. I mean, Jupiter has an enormous influence in its environment. So to give you a sense of that scale, here's Jupiter right here. It has an internal dynamo, so it's generating a permanent magnetic field, and those field lines come out of the pole, and they pervade the space around Jupiter, forming a bubble called the magnetosphere. Okay, so this is the outer boundary of the magnetosphere. That's essentially the last field line coming out of Jupiter. And essentially, you can see that Earth and its magnetosphere fits inside of Jupiter. Now, if this were visible to the naked eye, it would be the largest structure in the night sky. Okay, so far larger than the sun. Now, this sort of subsolar point of the magnetosphere, how far out does it go? And I should mention the sun is here. The sun is blowing off what's called a solar wind, which is a stream of plasmas, so a stream of charged particles. So that's different from solar radiation. It's blowing a stream of plasmas called a solar wind from left to right, and that is impinging on the magnetosphere of Jupiter and all the other magnetospheres of the planets. And so the magnetosphere is so strong that it stands off the solar wind at a distance that is about 100 times the radius of Jupiter. Now, does anyone want to take a guess how far back the magnetosphere goes away from the sun? Sorry? Saturn. Yeah, very good. Well done. It goes as far as Saturn, yes, and it was actually detected, by a spacecraft flying past Saturn and connected all the way to Jupiter. So it's an absolutely enormous structure here. Okay, now a couple of differences to Earth. As I mentioned, it's very large magnetic field, very powerful. It can stand off the solar wind at vast distances. And in addition to that, it's a very fast rotating magnetic field, and that's because a day is about 10 hours long at Jupiter. And it's also filled with charged particles. And those charged particles start their life at Io, which is Jupiter's innermost Galilean moon. And essentially, Io releases about 1 ton per second of volcanic material. And I'll show some very cool images of Io. Why is this important? Is because these charged particles interact with the magnetic fields, and they give rise to the auroras. So the auroras at Earth are driven by the sun, the solar wind. Jupiter's distance, you can't rely on the sun to do much, but there are other things that sort of kick in and fill in the void to a much larger extent. Okay, so here's just an artist impression again of Juno. And what I want to emphasize on here is that we go over the poles, and the remote sensing images take pictures of the aurora at different wavelengths. The different wavelengths tell you different things about different species and different depths. But in addition to that, more crucially, something we can do for the first time is that these in situ instruments can measure the magnetic field and charged particles on magnetic field lines that directly connect to the auroras. These charged particles travel along the field line. The reason why they end up in the poles is because the field lines funnel into the pole. Okay, so they're like the highways. And so by measuring those charged particles and fields, we can actually understand what acceleration processes and where the energy is coming from to power the auroras below. So I mentioned all planets have auroras, and I didn't show Earth's auroras here. I'll just kind of stick to the outer planets, but they've all been observed except Neptune's, actually, because it's just too far away and a bit too faint. But you can see that the auroras have been observed from both Earth-based telescopes. So this is from the ALMA telescope, that as well, and this is from the Hubble telescope in the ultraviolet. These are in the infrared, and also from spacecraft. So this is Juno, end of 2016, I believe, Jupiter's southern aurora in the infrared. So many beautiful structures here. And then Saturn from the Cassini spacecraft. This was in the ultraviolet in about 2010, I think. And this was the only spacecraft measurement of Uranus's aurora from Voyager 2 in the late 80s. And you can see that the auroras of Jupiter and Saturn kind of have this sort of classic band of light encircling the pole, but you can see at Uranus it is incredibly patchy, because Uranus is a bit odd. It's on its side. If you don't believe me, you can see a beautiful James Webb telescope over there. If you look at Uranus, the rings are looking at you. So it's on its side, but not only that, the tilt, so maybe I'll use my laser pointer right there. So not only it's on its side and it's orbiting around, but the magnetic field dipole, so you can think of the magnetic field as a bar magnet, it's offset by about 90 degrees, okay? So it's rotating and the field is tumbling, and so the auroras aren't at the poles. The question is, where's the pole? I mean, the pole is about 90 degrees difference between true north and magnetic north. So good luck using a compass in Uranus and finding your way around. Okay, so going back to the way the auroras are generated, I'll give a sense of what it's like at Earth. So as I alluded to earlier, you have the solar wind. That's the stream of charged particles traveling at about 400 kilometers per second. The solar wind is essentially an extension of the sun's atmosphere. So the sun is a dense ball of plasma. Plasmas are charged particles, so it's the fourth state of matter. So even though they rarely occur naturally on Earth, they actually account for 99% of the visible universe, okay? So much of everything around us is plasma. And just due to the very large pressure gradient between interplanetary space and the sun's core, you have a pressure gradient that will drive this wind radially away from the sun. It will pervade the solar system, and it will meet every planet's magnetic field. And when the conditions are right, that plasma can access the magnetosphere of the planet. And when it does, it will find its way to the poles, because again, they will follow the field lines, and the field lines funnel into the poles, and they will crash into the atmosphere, precipitate, and give off their energy to the atmosphere, which will then give off an emission. Now, as I mentioned, at Jupiter, that is not the case. We're just too far away, yet it does boast the most powerful auroras in the solar system. Now, how does that happen? So here's an artist's impression in 3D of the magnetosphere. Now, it is so large, as we said, it goes to Saturn, and it goes very far away towards the sun. But crucially, the Galilean moons of Jupiter, so Io, Europa, Ganymede, Callisto, their orbits are permanently embedded within its magnetosphere. So that's not the case with our moon. Our moon's orbit is almost always outside Earth's magnetic field. Sometimes it dips in and out, but almost always it's outside. These are always under the influence of Jupiter's magnetic field. Now, Io is a very, very hostile environment, arguably the most hostile in the solar system. So has lots of volcanoes distributed across, and it is continually exploding and releasing lava into Jupiter's environment, so in the form of sulfur dioxide. Now, those sulfur dioxide molecules, about a ton per second, they become ionized. So actually due to the effects of solar radiation, but they also bombard with other particles, and that strips off an electron. Now, when they become ionized, they then begin to feel the magnetic field of the planet, because otherwise as neutrals, they don't care about them. Now, when they do that, they start to rotate with the planet because they get locked into the magnetic fields. And over time, those plasmas start to diffuse outwards, and from various processes, they find their way into the poles of Jupiter. So the auroras of Jupiter actually starts life at Io rather than from the sun. So this tiny moon captured in Jupiter's orbit essentially accounts for the most powerful auroras in the solar system. So the other planets, I'll talk a bit about Europa and Ganymede as well. Ganymede is also a very interesting moon because it's the only moon we know of that has its own internal magnetic field. It has its own dynamo. So if you were to walk on the surface of Ganymede, you can actually find your way around with a compass, which might come in handy one day. Now, what's also nice about Ganymede, you can see it's a magnetosphere within a magnetosphere. And so it also has its own auroras, its own polar auroras as well, because its own magnetic field funnels charged particles into its poles. These moons are not so massive, but they're large enough to have a thin atmosphere. And by having a thin atmosphere, they can support auroras. Okay, so other than being beautiful displays that we can watch all day, as the Hubble spacecraft has for a very long time, there must be a reason why we care about the aurora. There must be a reason why NASA funds auroral physics. Now, for the outer planets, we learned a lot about Jupiter's environment, about its moons, about its magnetic field, just by looking at the auroras through the Hubble Space Telescope, which orbits the Earth. And that's because essentially the auroras, you can think about magnetic field lines coming out of them and mapping into hundreds and thousands of miles of space. So here, for example, there's an invisible field line that starts at Jupiter's northern atmosphere and maps all the way out to Io. Okay, so just by looking at that, we can understand, looking at a static picture or looking at a series of images, we can get a sense of the whole entire region about Jupiter. So we don't have to be everywhere at the same time. Okay. And you can see, for example, we get some information about Io, we get some information about Ganymede, we get some information about Europa. And by studying how the brightness changes and how the morphology changes, that essentially is a manifestation of how the atmospheres of those moons are changing over time and how they respond, for example, to being in eclipse. So when Io is behind Jupiter and it isn't getting any solar radiation, they believe that the atmosphere collapses, and you can see that manifested in the aurora. So it's a mosaic of everything that's going around Jupiter, and it also tells you a lot about what's going on in the atmosphere as well. Sometimes it's just difficult to see the atmosphere in the optical when you're so far away, but in the UV you can see these sort of swirls, and that gives you a sense of what's going on in the poles. Now, another maybe more, not necessarily a more important reason, but a reason essentially in the sense that it's broader, that we can learn something more about planets and exoplanets other than Jupiter, is the so-called energy crisis. Now, as I mentioned, Jupiter is so far away from the sun, and so if you were to model its atmospheric temperature based on the interception of solar radiation alone, you would estimate something that is maybe less than 200 Kelvin. Okay, and I should say that in the x-axis we have temperature, and in the y-axis we have altitude. So we're going down, and you look at the upper atmosphere here. Solar radiation models tell you that it should be less than 200. But we know that it's actually much higher than that, not only from images, but actually when Galileo flew past, it dropped in a probe, and it was able to measure the temperature with altitude. And it measured what was surprisingly about 4.5 times hotter than what it's supposed to be. And this is not unique to Jupiter. Actually, all of the outer planets, which we know Saturn has a powerful aurora, we believe Uranus has, and we believe Neptune has, all of those outer planets have a much hotter atmosphere than they would with solar radiation alone. Further evidence to demonstrate that the aurora is the result is if you were to look at Jupiter from above, and you were to measure the temperature in the infrared, you can see that where the auroras are, you get a big hotspot in temperature, and then there's a very smooth gradient as you're going into the equator. So essentially the energy is coming from the poles, the heat is being dumped from the poles, into the poles, and then they're getting redistributed equatorward smoothly from the planet. So this really kind of changes the Goldilocks regions of not only our solar system, but also stellar systems as well. So if you're thinking about planets that want to have sort of a moderate climate and you're expecting a certain temperature, it isn't enough to just look at how far they are away from their host star. It's important to take into account the fact that they have magnetic fields and therefore auroras, and that needs to be factored into your calculation when making estimates of their temperature and try to understand how their climate's driven. Now, fortunately, we can measure magnetic fields without even going there. Jupiter's magnetic field was discovered far before a spacecraft flew past, and that's because it beams off radio waves, which we can actually measure from Earth, and it was measured in the 50s, and you need a magnetic field in order to generate radio waves. That's also one facet of auroral generation. So by picking up radio waves from exoplanets, we can infer that they have a magnetic field, and better predictions can be made about heat, temperatures, atmospheric circulation, so on and so forth. Okay, now moving on to the extended mission. So when Juno was proposed, it was supposed to undertake about 35 orbits. So we're looking at Jupiter from the side. So it's coming round, going very close, then back out, and incrementally going step in this direction. And fortunately, the spacecraft's health was in great condition. The damage from the radiation belt wasn't as bad as it was expected to be. Actually, it was hardly a knock. And that meant that we could actually extend the mission and propose it to go further from 35 orbits into 76, so more than twice. And what was nice is that given that the orbital plane is evolving in this direction, what that means is that whenever Juno crosses the equator, it's doing so at distances closer and closer and closer to Jupiter. So that essentially has opened up opportunities to fly past 3 of the 4 Galilean moons. Okay, so I was involved in the planning of the flyby of Ganymede, Europa, and Io, looking at what kind of measurements we can make. It wasn't terribly straightforward in the sense that Juno was designed to look at Jupiter. So the instruments were there to make measurements at Jupiter. So we had to think creatively about what is the best science we could do given instruments that were designed for other purposes while looking at these 3 moons. So the first flyby, that was Ganymede. This was the image taken of Ganymede in 2021, in the summer of 2021. This was a very, very exciting moment. So it looks like nothing much is going on, but there's a lot going on both outside and inside. So for one, Ganymede is the largest moon in our solar system. It's actually larger than Mercury. So it's pretty much a planet, okay, going around Jupiter. And as I mentioned, there's so much going on here that's invisible to our eyes, and that's because it has its own magnetic field, okay? But then also the interior, it's believed to contain more water than all of our oceans combined. So Ganymede is essentially an ocean world. I'll talk a bit more about a future mission that's on the way to Ganymede, and also how do we know that there's water beneath the surface? And this was discovered actually late 90s, early 2000s from fields and particles instruments. Europa flyby then occurred in September 2022. So Europa is also another ocean world, and actually there's a spacecraft, NASA spacecraft Europa Clipper, which will be on its way to Europa towards the end of this year and make successive flybys. It's believed to actually have plumes, so the ice crust is believed to be quite thin, and there's a lot of crosstalk, if you like, between the interior and the space environment. So it really opens up doors to look at possible areas of habitability in our solar system. Then here's Io. This was just, trying to get it right, 2 or 3 weeks ago. So this is just fresh out of the oven. And I mentioned that there are volcanoes there. So there were 2 flybys of Io, so it was a real treat. One was end of December, and the other was early February. And the second time we flew past, we were able to see double volcanic plumes. And these are the volcanoes, so you can get a 3D sense. What's quite cool is that the height of the volcanoes can be measured by looking at the shadow patterns and the angle of the sun with respect to Io. And they're believed to be larger than Mount Everest. So in absolute terms, okay, so not just relative to Io's radius, which is much smaller than the Earth, but in absolute terms, they're much larger than the Mount Everest. So if you don't believe me that these are volcanoes, and if you think that this is just a fuzzy picture, here's what it looks like in the infrared. You can see that it's just full of lava. I mean, it's a very, very, very scary place to go to. And really, this little moon that's orbiting very close to Jupiter, essentially, you think about, you do the whole sequence of events, starting from these volcanic activities to the enormous temperatures at Jupiter of its aurora. Everything starts here. So the tail is wagging the dog here. Okay, so why do we care about moons in general? By the way, I should say there's no ocean in Io. It's just too much of an inferno to have any liquid water. But there's still some debate as to whether there's a global magma ocean beneath its surface or if there are just pockets of magma that connect to the volcanoes above. But generally, we believe that there are many moons in the outer solar system that have liquid oceans beneath them. And how do we know they're liquid oceans? Actually, the first discovery was of Europa. This was when the Galileo spacecraft flew past Europa. And since it had a good idea of what the magnetic field would be of Jupiter's environment, it knows what the magnitude should be, what the direction should be. If you think about a field line coming from the north to the south, you can have a model. You can predict that if I'm here, the field should be pointing, say, in that direction, about to turn around and go to Jupiter. But once the spacecraft was flying past the moons, the magnetic field was measured to wiggle a lot, and change in both direction and magnitude. And so the only thing that could explain that was a liquid ocean beneath the surface. So how does that happen? These oceans are salty, they have a conductivity, and these moons essentially, as I mentioned, they are permanently immersed in Jupiter's magnetic field. So you think about Jupiter's magnetic field sweeping past these moons. So you have a time-varying magnetic field, and you have a liquid ocean, which is a conductor. So that's going to give rise to a current, and that current is going to flow to try and screen out or shield that time-varying magnetic field. And that was the best and really the only explanation that the scientists could give back at the time, that it's an ocean. And so, one could ask, well, there are other conductors like an iron core, but the conductivity is about 6 orders of magnitude difference, okay? So the conductivity of a liquid ocean is about 1 Siemens per meter, and iron core is about 10 to the 6. So that large order of magnitude difference means that we could get some really, really, really good constraints there. Now, successive flybys, the evidence was just building more and more. So made charged particle measurements. And what were they measuring? They were measuring H+, O+, OH+, all these water group ions that have started life as H2O. Then images were taken as well. And, they could see ice shells. There was some spectroscopy done. And everything sort of points to liquid oceans there. And the evidence is so strong, and scientists are so convinced that there's a $1 billion mission at the end of this year heading to Europa to get a better characterization of the interior. Now, the question of habitability, this has really revolutionized that, because for very long it was thought that you can only look for life in the so-called Goldilocks zone. So you shouldn't be too close to the sun, because then water would evaporate, and you shouldn't be too far away from the sun, because water would be frozen. And that is true only if water existed on the surface. But actually, as we can see here, water can exist beneath the surface, and you can have a lot more water than we do, like Ganymede does, for example. And the reason why the water is kept liquid is because due to tidal heating from Jupiter's gravitational field, but also there's antifreeze as well. So there are ammonium compounds that act as antifreeze to keep the water liquid and to keep them flowing. So there are 4 boxes you need to tick for habitability. One's water, which is check. One is energy. There's tons of energy, which is check. And one's hydrocarbons. There have been lots of hydrocarbons that have been measured to the limit of the instruments. So now better instruments and spectrometers are going to try and measure longer chains of hydrocarbons. So that's also check. And then the 4th is stability, which is still unknown how stable these are. Now, when I say habitability, the word life may come to your mind, but that's not necessarily what I'm saying. It's just that the conditions might be right for life. So that could mean life could form, maybe simple life exists, or maybe life once existed. But the ingredients are there in the cauldron for life. Now, Ganymede also, it's a little bit more difficult to characterize the interior. And that's because when you measure a magnetic field as you're going past the planet, you're measuring a vector sum, okay? So this is what you're measuring. So that means I'm flying past Ganymede, I'm measuring the field of Jupiter, so-called interior and exterior, doesn't matter what these are. And then I'm measuring the field of Ganymede, which is a dynamo of Ganymede. Then I'm measuring the field due to the currents from Ganymede's environment. And I'm also measuring the field of the ocean. So separating that is a challenge. And the only way to fully characterize and separate all of these out to get a full understanding of B ocean is to send a spacecraft to orbit Ganymede. And this is where the JUICE mission, it's on its way. So it launched April 2022, and this is a European Space Agency mission. So it's our first mission to the outer solar system, and this will be the first spacecraft to orbit a moon other than ours. So as you can tell, in my field, it needs a lot of patience. So when I'll see the first data will be about 2031. That's Jupiter orbital insertion. We'll go into orbit around Jupiter, make a couple of flybys of Europa and Callisto, but then go into orbit around Ganymede, which I think is incredibly exciting. And having that sort of long-term probe of Ganymede's magnetic field, they'll be able to essentially decompose the measurements and have better, more precise constraints of the interior. And then, of course, as I mentioned, that Europa Clipper is also on its way. So it's a very exciting and very long road for outer planetary science. And I'll leave with, this is an image of, not a real image, but an artist's impression of Cassini spacecraft, which crashed into Saturn's atmosphere. It was, in its final days, it was conducting orbits between Saturn's atmosphere and its inner ring. And it was a real privilege to be at JPL to witness the final blips that was coming back from Cassini. So yeah, thank you all.
Right, questions? All right.
You said the one with the Europeans, 2031, 2032.
Yeah.
What is the one we're sending, you said, coming up?
All right. Okay. So, so there are two missions going to Jupiter. JUICE launched in 2022, and Europa Clipper will be launched, I believe, November this year. Yeah. Actually, before JUICE. Yeah. But, you know, that's just the way the planets are aligned. Yes, so it'll get there not too long before JUICE. But what's also very exciting is for the first time, we'll have two spacecraft orbiting Jupiter so we can make multi-point measurements as well. Yeah. Looking at a certain feature, maybe that's being transported from one side of the magnetosphere to the other, and we can have the two spacecraft measuring it, or we can have one spacecraft measuring, say, charged particles on the field line, and the other, say, looking at the aurora, getting a more spatial understanding. Yeah.
Both hands went up.
Think here, yeah.
So let's go with you first.
So you said radio waves from spacecraft are used to measure the perturbations in the gravitational field. Are those from components that are, or I guess where are those radio waves coming from on the craft itself?
Oh yeah, so there are antennas. They have a high gain antenna, and few times a day beams back radio waves to the Earth, to the deep space network. So there are 3 of those around the Earth, and that's essentially to receive data and to talk to the spacecraft and to send commands. Yeah, so it's not an add-on to measure the gravity. It's just by looking at the frequency of those waves and seeing how they shift and that gives us a sense of what the Doppler shift is. So as the space, and the Doppler shift is essentially the wavelength will stretch when you're moving away, and then sort of, red shift and blue shift.
Was that in the original plans, or was that like?
Yeah. I mean, this is it was done for Saturn as well. Yeah, it's a well-used exercise in the outer planets. Yeah.
How big a shift do you measure?
In wavelength? Oh, I don't know the number, but very, very small. Yeah, it's very, very. Yeah, I mean, this may have to go back a few slides. So this is a very, very, very delicate task. Yeah, because of course there's noise in the data, and you want to be sure that the signal you're picking up is above the noise. But yeah, it's very, very delicate.
So I could add to that, the DSN, the Deep Space Network, they can measure accelerations down to, 10 to the -8 kilometers per second squared.
Wow.
So,
Wow, that's incredible.
but it takes a lot of processing to get there.
Yeah.
A couple different questions with this slide. Is it known for sure, or is it still kind of up in the air whether or not Jupiter has a solid core, and if so, how big it is?
Yeah, so there are two schools of thought about it, whether it's a solid core or something a bit more mushy. So not a solid core with a defined boundary, but something that's sort of a little bit more of a fuzzy core. Yeah. It's really pushing to the limits of the models at the moment. But yeah, at the moment, there isn't a very strong consensus in one over the other. But it's basically boiled it down from maybe a dozen hypotheses to 2. Yeah.
You mentioned magma on Io.
Yep.
So it turns out, Enceladus around Saturn has geysers, and they're
Yeah.
Enceladus is cold. It's not hot.
Yeah.
Okay,
Right.
but is Io actually hot?
Yes, Io is very hot. So Enceladus, so those geysers, that's water. So it has a global ocean beneath its surface, and there are cracks. There are fissures, which are very cool because and I know I'm moving a bit to Enceladus, and I'll come back to Io in a moment, but the tidal effects are so extreme because these are very, very large planets, and they're orbiting quite close to the planet, but they have very, very small orbital eccentricities. So that means it's not perfectly circular. Sometimes it's a little bit closer to Saturn. Sometimes it's a little bit farther away. And the fissures open and close, depending on whether you're close. You have sort of that push-pull effect. And so the geysers that come out, and you can see that in cameras, and you can see a nice plume coming out of Enceladus. And actually, it wasn't discovered using images, it was discovered using the magnetic field instrument, because when Cassini flew past Enceladus, they saw wiggles in the magnetic field. And that's essentially because when those plumes are ejected from Enceladus, they become ionized and charged, and they interact with the magnetic fields. So the fields were wobbling. So Cassini went back and said, okay, maybe this time we should actually point our camera specifically, and lo and behold, the plume was there. But Io, yes, it is magma. Yes, it is magma, sulfuric stuff, as we know. Yeah.
Question for you. So one thing that we have seen with the Earth, right, is that you can have magnetic reconnection, right?
Yeah.
In this instance. So what is that? Does that have a similar manifestation with Jupiter, and what does it look like? I mean, what would make it different? Because you have a much stronger field, right, with Jupiter. So does it manifest differently? What does it, and where would we perceive that as well? So
Yeah. So maybe I'll just say quickly what magnetic reconnection is. So essentially, you get the aurora. Maybe I'll use this here. So I'm showing the solar wind that's blowing away from the sun. Embedded in the solar wind is the sun's magnetic field. Okay, so it actually, as you have the sun's atmosphere extending away, it's dragging along, since plasmas are tied to magnetic field, it's dragging the sun's magnetic field with it. So that's called the Interplanetary Magnetic Field, or the IMF, okay? So it's not the International Monetary Fund. Now, what happens is that the magnetic field of the sun kind of changes, the reasons why, but typically you can get lots of turbulence occurring. And you can imagine a situation where the magnetic field of the sun is pointing south, and the magnetic field of the Earth goes from south to north. So that means that the magnetopause of the Earth, it's northward, and that southward solar magnetic field and northward Earth magnetic field come together and they reconnect. So that's called magnetic reconnection. And that opens up the field, and plasmas get access into the magnetosphere, and then that stored magnetic energy gets converted into kinetic energy, and the plasma essentially shoots off as a jet, as I mentioned, finds its way into the poles. Both the evidence for magnetic reconnection at Jupiter is weak, plus it is understood that it doesn't have much of an effect, especially not because it's not an explosive process like it is at Earth, but it pales comparison to the energy from Jupiter's rotation and its interaction with Io. That pretty much washes out on the aurora, it washes out any signature you would expect to see from magnetic reconnection. So that's one thing. Another thing is that also the conditions aren't conducive to magnetic reconnection in the outer solar system. And that's because you have what's called the Mach number. So that is essentially the ratio between the solar wind speed and some characteristic speed. And magnetic reconnection is promoted when your Mach number is low. But when you go out to the outer in the solar system, the solar wind speed is pretty much constant, but your characteristic speed goes down. So your Mach number goes up. And you have very, very powerful shocks. And that is not good for magnetic reconnection. Yeah. So we think it doesn't happen so often. And when it happens, it may be quite strong compared to Earth, but nowhere near as strong compared to the other auroral energization mechanisms that occur interior to Jupiter's magnetic field. Okay.
So first, I'd encourage anybody under 30 to ask questions. But you had said that the Juno mission was sort of the limit of what a solar-powered mission could be.
Yeah.
Right. So, is basically the power consumption of the mission what you're getting from the sun at the time, sort of in a steady state, or do spacecraft scientists, right, charge up their spacecraft all the way out as it's traveling to Jupiter? Are you sort of in a steady state that you could live as long as those solar cells live?
Yeah. So, well, first of all, they have to be quite gigantic to get a very massive effective area. But they degrade over time, especially getting knocks from the radiation belt. But usually they generate more power than the instruments need. And there are a couple of manipulations that can be made to manage the power consumption, certain instruments being turned off. But then there are also situations where Juno goes behind Jupiter, and that's quite problematic because it then doesn't intercept any solar radiation. And so we have to rely on the charging, essentially from the surplus energy stored from the solar cells. Yeah, but yes, they do generate more energy than it needs, but oftentimes the demand the supply goes down, and we need to keep the instruments going. Yeah.
Just out of curiosity, I may have missed this, but did you say what specifically you worked on in the Juno mission?
Yeah, so I'm involved, I spend most of my time analyzing data from this instrument, the WAVES instrument. So the WAVES instrument measures so-called radio and plasma waves. And you can think of those as, so I mentioned that you have magnetic fields in space and you have electric fields. these antennas measure fluctuations in those magnetic fields. So they measure essentially the wiggles in the magnetic field. And the reason why we're interested in those fluctuations is because that's where the energy is in those electromagnetic fields. So the energy from those fields gets transferred to charged particles. Then those charged particles get accelerated into the aurora. Okay, so yeah, I spent most of my time analyzing data from here, and I'm also involved in the planning for the flybys of the moons. Well, no longer because Io was the last flyby 2 weeks ago, but sort of leading workshops on understanding the data, publishing the data, getting the data out there. Yeah, but mainly the science comes from this instrument, but I do work with the other instruments as well, because no one instrument can tell you the whole story.
So the moon you missed was what, Callisto?
Yeah, there was no Callisto flyby.
It can't be done, or
No, it can't be done. Just so one thing, I guess, this image misses out. This image misses out on the 3D effect. So it's true that as the orbits go by, you cross the equator closer and closer to Jupiter, but then the moon needs to be there when you get to Io's orbital location. And that just doesn't work out for Callisto. So I think we were extremely fortunate that it's designed in such a way that Europa and Io were there when we got to their orbital location. Of course, there was some manipulation made, but it's very limited because each time you do that, the reason why these are color-coded is because the orbits are shortened as we go past each of these moons. And so it comes at the cost of some propellant. So yeah, that just wasn't possible for Callisto. But JUICE will make a couple of flybys past Callisto. I'll just add one more thing, that JUICE will fly past Callisto. JUICE will orbit Ganymede. Europa Clipper will fly through Europa many, many times. And we probably won't see any Io measurements in our lifetime. There's no future mission going to Io. So the last that came out of that was, like I said, fresh out of the volcano 2 weeks ago. Yeah.
So you've talked a lot about the strong magnetic fields. There's a lot of charged particles flying all over the place. Synchrotron radiation is a natural thing to wonder about. So I've always wondered, is there the possibility of looking remotely at the whole system and looking at synchrotron radiation and actually kind of sensing the whole dynamics of the magnetic fields and all that sort of thing?
Yeah. So there's a radiation monitor at Jupiter as well, which gives us an image of the synchrotron radiation, and also the microwave radiometer as well. But that's not a sort of leading science objective at Jupiter. So I know that there's a small team that is working on it. But then again, since it's not a leading science objective, we don't have that sort of wealth of instruments to look at the synchrotron radiation. The radiation monitor was built to actually just monitor the radiation environment. So it can tell us when things are getting a bit too hot with the radiation belt. So the amount of science that we can pull out of that is quite limited.
Well, I'll ask the last question because we're almost there. How much of the orbital decay is of Juno being caused by atmospheric drag? I mean, is the atmosphere like Earth where it sticks out, or is it just a crisp end?
Yeah. I don't know how much exactly, but I imagine going that close to Jupiter, things have to be changed quite a bit because of the atmospheric drag. I'm just guessing here. I think it's an important effect. I just happen to have heard a lot about it with Cassini when it got very close to Saturn. And actually, eventually, it was that which, changed the orbit forever. Yeah, when it got it was designed to be kicked by Titan, but then have a periapsis low enough that the effects of drag would be so significant that it wouldn't be able to fly off one more time. Yeah. So I imagine being close. I mean, we measure the ionosphere, so there must be some effects of drag, and it must be tolerable. But I don't know how much. Yeah.
I'm guessing that's part of what's changing the orbit and causing it to decay, but anyway.
Yeah, well, what's changing the orbit mostly is the inhomogeneities in the gravitational field of Jupiter. So Jupiter's polar flattened, so it's bulged at the equator and a little bit flat at the poles. So the gravitational field is non-uniform. So that causes changes to it. Otherwise, if it were a perfect sphere, you would just expect it to remain preserved. Yeah.
All right, let's thank our, I mean, we're at 4:30, so let's thank our speaker.
Okay, thank you. Thanks.
Thank you very much. That was a really, really great talk.